Hello everybody, and welcome back to another CIV E 398 assignment tutorial. In this tutorial we're going to be covering assignment 6, question number 2, which again focuses on the elasticity tensor. So if we have stresses we can determine the strains, or if we have the strains we can determine the stresses. And in question 2 it says, the Cauchy stress at a point inside a continuum is given by, and it gives us our stress tensor sigma. So what's nice in this question, unlike question number 1, is we're given the full stress tensor. So we have sigma 1, 1, 2, 2, 3, 3, and we have all the shear stresses too. So we have sigma 1, 2, sigma 1, 3, and sigma 2, 3. And the question says if E is equal to 150 GPa and V is equal to 0.2, so that's the Young's modulus and the Poisson's ratio respectively, determine A, the principal stresses and their directions, B, the principal strains and their directions, and C, if the principal stresses and the principal strains are aligned. So the key here is going to be finding the principal stresses and the principal strains. And we know in order to do that, we're going to need the stress tensor and the strain tensor. Now, if we look at part A, the principal stresses, well, we're going to need the stress tensor, but we're given the stress tensor. So part A should be a nice little review because it's just going to be what we know before. Now, part B is going to get a little different because in order to find the principal strains, we need the strain tensor, but we're not given the strain tensor. So we're going to have to use our elasticity tensor to convert our stress tensor into a strain tensor, and then from there we can find the principal stresses. However, before we get into that, let's figure out, okay, well, how do I determine these principal stresses or principal strains? Well, the process for them is identical, so I'm going to show you guys how to find the principal stresses, and you guys know that we can apply the exact same process to the principal strains. So to determine the principal stresses, which I call lambda, we need to solve the following equation, where the determinant of sigma minus lambda I is equal to 0. So in this case, sigma, that's going to be my stress tensor. Now, again, you guys are all going to use Mathematica. This whole assignment is basically one giant Mathematica. I can't even say that right. One giant Mathematica assignment, so you guys will be very familiar with Mathematica by the end of this assignment. So we know in Mathematica, if I want to find the principal stresses or principal strains, that's just going to be the eigenvalues of my tensor. So all I have to do is define my tensor, which I put m is equal to, and I put all the components. So if m was my stress tensor, all I have to do is go eigenvalues of m to find my principal stresses. Now, if m was my strain tensor, I do the exact same thing where I just go eigenvalues of m, and that'll give me my principal strains. Now, of course, we're also concerned about their directions. So if we want to find principal directions, which I call P, we need to solve the following equation where sigma P is equal to lambda P. So of course, the lambda in this case are going to be my principal stresses. The sigma is going to be my stress tensor, and P right there, that is going to be my direction. So again, we can realize that, wait a second, P is just simply going to be the eigenvectors. So again, if I'm in Mathematica and I have my tensor defined as m, all I have to do is go eigenvectors of m. So if m was my stress tensor and I go eigenvectors of m, this will give me the directions of my principal stresses. If m was my strain tensor and I go eigenvectors of m, this will give me the directions of the principal strains. So nice and easy. This is just review. You guys are already experts. So if we look back at the question, we basically want to find the principal stresses for the strains and the stresses. Now, we have the stress tensor, so we can jump right away and find the principal stresses and their directions, no problem. However, we don't have the strain tensor, so we can't exactly find the principal strains quite yet. So the only trick to this question is realizing that we can convert our stress tensor into a strain tensor using the following relationship. So for a linear elastic isotropic material, and that's going to be the key here, is it's an isotropic material, we can convert from stresses to strains using the following elasticity tensor. So just like before, we can see that even though it looks really gross, it's basically going to be just two components. And you guys are saying, hold on, wait a second, Clayton, I see three components. I see V, E, but I also see a G down there in the bottom right corner. Well, let's look at these three components. So when we consider V and E, well, those are nice, easy, good to go, because we know them. Now, you're going to say, Clayton, well, I don't know G. Well, of course, we know G. G is the shear modulus, and it's simply a function of V and E. So since we know V and E, we can easily find out what G is. Now, this is the exact same spot we had in question 1, but we encountered a problem where we were using this elasticity tensor, but we didn't know all the components of our strains. However, in this case, we're very lucky because we actually know all of our stress components. So if I were to look at the right-hand side of this equation, the first thing I have is my elasticity tensor. I know absolutely everything in there, good to go. And then the second thing, of course, is my stress vector. Well, that's just all my stress components. And luckily for us, we know everything in there as well. So this whole right-hand side we know, we can solve for it. And with that, we can find our strain vector over here. So you guys are thinking, well, hold on a second. This is a very rare occasion where we have a nice formula, but in this particular case, we know everything on one side of the formula. So too easy? Is there any tricks? Well, the answer is actually no. This question is a very simple question, but there is one little trick that a lot of students will forget, and it will cause a lot of problems. And that is right here, the shear strains. The shear strains. So I'm going to say that again, the shear strains. Well, why is this a problem? Because of that 2 out in front. So keep in mind that when we're finding the eigenvectors and eigenvalues of a tensor, well, we need a tensor. And when we find these strains, we're given a strain vector. So what we're going to have to do is take the strain vector and fill out our strain tensor. Now the problem is all of these shear strains are actually 2 times whatever the actual strain is. However, students won't realize that, so if they get the entry in this vector as, let's say, 0.5, they will enter 0.5 directly into the tensor. However, we realize that the strain isn't 0.5, 2 times that strain is 0.5. So the actual shear strain here would be 0.25. We have to divide by 2. So that's the only thing that you guys are going to have to really keep in mind in this question is when we have our strain vector and want to convert it into a strain tensor, we have to remember that there is a 2 out in front of all of those shear strains. But of course, after we have that tensor, we can easily throw it into Mathematica to find our principal strains and their directions. And then that's basically the rest of the question because we already have the principal stresses. Now we have the principal strains, which is part A and B. And then part C will simply be asking to comment on whether the directions are the exact same. Now, I'll kind of spoil it for you guys. The directions in this case will be the same. It's a linear elastic isotropic material. However, I want you guys to keep in mind that this is only for an isotropic material. If I had an orthotropic material, as you guys will see, the principal stresses and the principal strains may not be aligned. So don't always think that they will be aligned because Dr. Sammer can easily pull the little sneak attack where in an exam he gives you an orthotropic material, asks the same type of question, you guys will go, oh, well, an isotropic material, they are aligned, so they must be aligned for an orthotropic material. Well, the answer is no, for an orthotropic material, they may not be aligned. So just a little hint for the final exam, or I guess midterm, whatever this will be on. All right, guys, that concludes question number 2. Should be a nice, easy question. Thank you guys all so much for listening. I will see you guys in question number 3.